welcome back, and it's been a hot minute since the last vacuum tube computer episode, but when I say it's been hot, I mean it quite literally. Texas just went through one of the most brutal summers it's seen since 1980, essentially. It was just obscenely hot outside every day for like 3 months straight, well, I'm at a point on the vacuum tube computer build where I have to cut huge PCBs. In a previous episode, we actually we built this, which is one of our memory boards. There's 4 bits of memory on here, and we need to build 12 of these. But this is a single PCB that is nearly 500 millimeters wide, and cutting this on the mill takes about 4 or 5 hours, I think. It is really a very long cut, and when it is over 105 degrees outside or 40 Celsius, that is just brutal on the mill. The spindle motor gets really incredibly hot, and the CNC computer doesn't have any active cooling. It's all passive cooling. There's just a big heatsink that sticks out the back. There's no fans or anything on it. And so when it's sitting in the garage and the heat in the garage is well over 110, it can sometimes glitch out, and I get some weird display errors on it. So I just gave the mill a nice long summer break, but that meant that the vacuum tube computer got put on hold for a few months. But it started to cool down a bit, so I started spinning the mill back up, and it's time to get back to work on the vacuum tube computer. And so we have 4 bits of memory. I need to build a lot more of these. I'm not going to build all of those immediately though, because it's incredibly time consuming, but also I want to be able to test these with a 6-bit memory address to make sure that our addressing and decoding and everything is working correctly. So that's what we're going to focus on today, figuring out the addressing and decoding, how we're going to take that 6-bit memory address coming in and use that to address one single bit, no matter which one it is, to change the value of that. So let's hop over to the bench. We'll take a look at how 1 bit of a memory cell is set up in terms of X select and Y select. And then we'll take a look at a problem that I'm going to run into very quickly due to the sheer number of tubes that I have to address. And then hopefully we'll get something built by the end of the episode and give it a test. So let's hop over there and get started. Right, just as a quick reminder, this is the schematic for 1 bit of memory. So all of this schematic is represented by 4 tubes and a VFD in the middle here. So on this entire thing here, we've got 1 bit here, our 2nd bit here, 3rd bit here, and 4th bit over here on the end. And I still think it's really cool that we're using a 6AU6 and a 6977 as a kind of imbalanced SR flip-flop. But we've got a whole lot more than just 1 bit that we want to store. Ultimately, we want to store up to 48 bits. And so we're going to use a 6-bit memory address. And that means that we're going to have 3 bits for X select and 3 bits for Y select. So if we look at the bottom left of the schematic over here, you can see that we've got a write signal, an inverse write signal coming in. We've got an X select, a Y select, and then we've got a data bus in. Now, instead of looking at just the schematic here, it might be a little easier if we look at a logic diagram of it. So if we take a look at this page here, this is the logic diagram for essentially 1 row of memory. So we can see that this collection of 4 NOR gates here is going to be our D flip-flop. The 2 right here are going to be the SR flip-flop, so that's a 6AU6 and a 6977. And then the 2 right here are just for gating. And that actually corresponds to exactly how it's laid out here on the PCB. The first 2 6AU6s here are the 2 NOR gates here that are acting as our gating mechanism for the D flip-flop. The 6977 and this 6AU6 right here are the 2 that are set up as an SR flip-flop. And then the final 6AU6 is this big 4-input NOR gate on the end. And this is where it can get a little confusing, because that NOR gate on the end and the 3-input OR gate on the other side are what we're using as our selection logic. The 4-input NOR gate might be a little easier to understand. All of the inputs have to go low for the output to go high. If any single input is high, the output will be low. So the output from our SR flip-flop needs to be low. The write signal that's coming into it needs to be low. The X select needs to be low, and the Y select needs to be low. And that is actually why the VFD in our SR flip-flop is backwards. When the VFD is illuminated, it's outputting a high signal, which is pulling that output continuously low. So it's really important to note that in order for us to select one bit of memory, the X select and the Y select have to be low for that specific bit. And the reason I say that's important is that it means that the X select and Y select have to be high for every single other bit. So if we take a look at the logic diagram for the entire thing here, you can see over here on the far left, we have our 6-bit memory address coming in. 3 bits are for X select, 3 bits are for Y select. This works out really well to give us an 8x8 grid because 3 bits can address up to 8 different locations. So we have 8 X lines and we have 8 Y lines. And only where the X and Y lines intersect is where we're going to pull that value low, and that's the bit we've selected for either writing to or reading from. But what this means is that each X select line or each Y select line has to feed a lot of other inputs. So if we just take a look at the first X select line here, if it is high, meaning that we're selecting some other X row of memory, it has to feed 2 inputs per bit on that X select line, which means it's feeding 16 total NOR gate inputs. So we need to make sure that that X select line is very strong. And well, now we're running into a problem called Fanout. And I've talked about Fanout a bit before, but that was way back on the instruction register. And I think it's going to be good to refresh our memory on what Fanout is and how we can go about tackling it. All right, in order to understand the problem of Fanout, let's first take a look at how I build one of my NOR gates. This is just a bog standard NOR gate that I use pretty much everywhere on both the processor and the memory circuits. And it's just a 6AU6 pentode with a 33,000 ohm plate resistor, and then a 220K voltage divider that goes to negative 12 volts. The grid is pulled off of the center point of that voltage divider, and then the other side goes to 2 diodes, and those are our inputs. And I can put as many diodes as I want here for a multiple input NOR gate. Now, the way that this logic gate is going to work is that if any input is high, it essentially pulls the grid to a positive potential, which allows electrons to flow from the cathode all the way up to the anode. And when that happens, the potential of the anode is essentially going to be pulled down to a potential that more closely matches the cathode. And we pull our output directly off of the anode or the plate, and well, that's where we're getting it. If there's a high level coming in, there is a low level going out. Or conversely, if all of the inputs are low, the grid is pulled to a negative potential, which prevents any electrons from flowing through the tube, and the plate is then pulled up to 24 volts through the 33,000 ohm resistor. Now that 33,000 ohm resistor is going to effectively limit the amount of current that our output can supply. So if we imagine this output going directly into the input of another NOR gate, there is a bit of load on this output now, because this 220K together makes 440K, and that's going to negative 12 volts. And that's going to start pulling that output value a little lower. And well, if we have that output feeding multiple other inputs, well, those are now going to be sitting in essentially parallel. Each input is 440K, but if we have 2 inputs, that drops that total load on the plate down to 220K. If we have even more, it goes down to 110K. If we have even more than that, it drops it all the way down to like 55K. And that's gonna pull our output very low indeed. And so this is the problem of Fanout. How many other inputs can a single output drive? And I've got 3 vacuum tubes set up here to kind of demonstrate what I'm getting at. The one on the left here is set up pretty much exactly like this, only I don't have the diodes, and I just pulled it directly to negative 12 volts because I want to see our output at a logic high level. And coming off of the output, I'm going through a 100,000 ohm potentiometer because that's what I had. So we have essentially 100,000 ohms of resistance between the output and negative 12 volts. And I'm looking at what the value of the plate is. And we can see it is at 15.6 volts. And that is already too low. If the value of the plate gets to be too low, it's no longer a viable logic high. I need at least 18 volts as a logic high, preferably 20 volts. So seeing 15 and a half volts here is not good. And if I take the value of this potentiometer and I twist it so that it goes down to like say 70,000 ohms, or even all the way down to like say 50,000 ohms, well, you can see that our logic high is no longer a logic high, it's actually getting frighteningly close to a logic low now. For logic low, I like to have less than 6 volts. As a matter of fact, I can make my logic high here act like a logic low if I put enough of a load on the plate here. It's important to note that the tube is in cutoff. There's no electrons flowing through it. This should be a high value coming out of here, and we've got it all the way down to 3 volts. That is untenable. We cannot use that at all. So what is the solution? Well, it's adding another tube in the middle as a cathode follower buffer, which is what this schematic right here is. Now it's important to note that the way we were using the NOR gate, it was set up as an inverter. So a high input caused a low output, a low input caused a high output. But the cathode follower buffer is, well, a buffer. It doesn't invert it. A high level input gives us a high level output. A low level input gives us a low level output. But a cathode follower will not amplify the signal. It essentially is just duplicating whatever it sees on the input. Now coming off of the plate, I have a 100 ohm resistor here, but you don't actually even need a plate resistor. I just put it there because it actually makes routing the traces a lot easier on the PCBs because it acts like a jumper and I can run stuff underneath it. Now coming off of the cathode, instead of going directly to ground, we go through a 220,000 ohm resistor that then goes to ground. And then we pull our output directly off of the cathode. And it's called a cathode follower because the cathode elevates itself to whatever potential the grid is sitting at. But the big thing about this is that our output is only being impeded by the internal resistance of the vacuum tube, which is considerably lower than our 33,000 ohm plate resistor. As a matter of fact, in my internal testing, I've kind of come to the conclusion that the internal resistance of a 6AU6 at 24 volts is about 2,000 ohms. So I've got this second 6AU6 here set up as a cathode follower buffer, and I'm using a 50,000 ohm potentiometer, and you can see that even just at half of the resistance that our inverter was at, we're still at a rock solid 24 volts. There is absolutely no drop there. And so if I start twisting this potentiometer, boy, man, that's about halfway. We're down to about 25,000 ohms there. And you can see we only barely just started to drop below 24 volts. That is awesome. We've got a very strong output coming out of that. If I crank it all the way over, The 50,000 ohm potentiometer is now at 0 ohms. I just have a little 1K resistor here to prevent my potentiometer from burning up. But you can see we've gone down to, 10.7 volts or something like that, 10.6 volts. So even with just 1,000 ohms of resistance between the output and ground, we're still at 10 volts. That's pretty impressive. But I think we can actually do a little better. And that's what this third tube on the far right here is. This is a 6CG7. It is a dual triode, and it's actually essentially a 6SN7, I believe, which is a nice octal radio tube stuffed into a 9-pin package. I like it because it has a nice big plate for a triode. Now, compared to a smaller 7-pin pentode here, the plate doesn't quite have as much surface area as these 6AU6s do. So I'm not expecting one triode to actually be able to move as much current as one pentode. But because we've got two triodes in a single package, I can put them in parallel. And that should give me a little more heat and a little more surface area, which should let us move a little more current. So again, I've got my potentiometer set up here. This is at 50,000 ohms, and well, you can see we're sitting at 24 volts. Absolutely no problem. That's not surprising. If we go down to about, 25,000 volts, it's looking just like the 6AU6, still pretty much 24 volts. So let's crank it all the way. Let's go all the way off. We only have now a 1,000 ohm resistor to prevent me from burning out my 50K potentiometer. And well, you can see we're about 3 volts, 2.5 volts higher than we were on the 6AU6. So it is able to provide a bit more current. And then if we just give this just a little bit of a twist here, boom, we're straight up above 18 volts again. So the 6CG7 set up as paralleled cathode follower buffers can provide a lot of current, which is going to serve us well when we build our 6-bit addressing. So in order to build that, I need essentially to take the 6-bit address in, and I need to buffer it as well as invert it and then buffer the inverted signal and then have essentially 12 signals coming out, because we're going to use those 12 signals to go through OR gates to build our decoder. So what I want to build today is just that buffer, invert, and buffer circuit. And so I've got a design that I'm fairly happy with. Let's pop it on the mill and get it cutting out. And this is one of the biggest boards I've cut for this to date. It's a little bit longer than the memory boards, and it's actually a little bit taller as well. And this was about a 6-hour cut, and my time-lapse battery died about midway through the cut. But once the cut was complete, it all cut beautifully with the exception of the top left and the top right corner. I didn't quite get the right isolation going on up there. I think the PCB was maybe flexing on the mill and it didn't quite cut it right. So I've got to sit down with a knife and clean that out. And then once everything was properly electrically isolated, it was time to get it soldered up. And again, I fully charged up my GoPro and I started the time lapse of doing it. And it's such a labor intensive job to solder this up that it took about 4.5 hours to solder up. And again, my time lapse battery didn't make it. All right, and here's the finished board, and oh man, it came out beautifully. I am absolutely in love with how it looks. I love the staggered look between the 6AU6s and the 6CG7s next to them. And most of the 6CG7s, not all, but most of them have a side gitter. So the top of the glass is actually clear, and that's a really interesting look. I'm gonna dig through my collection and see if I can find nothing but side gitter 6CG7s and replace these with all side gitter ones, because I think that would be a really interesting glow coming out of the top of these things. Now I've got it hooked up to a little bit of a test circuit here to test it out. We've got 6 toggle switches on the right here for our 6 bits in, and then we've got 12 LEDs here split into pairs. So each pair is going to be the buffered and then the inverted and buffered signal coming out. Because I'm dealing with weird vacuum tube logic level signals. I've got a bunch of resistor dividers on there to get the LEDs to hopefully illuminate correctly. I genuinely have not put any power at all into this board until this very moment. I have absolutely no idea if it's going to go up in smoke. I am reasonably confident that it's going to be fine because they're fairly simple circuits, but I wanted the camera rolling just in case something did go up in smoke. So, well, here goes nothing. Let's flip the switch and see what happens. All right, now that it's warmed up, it looks like we might have a problem with this bit here on the end. The remaining 5 bits look like they should be working correctly. The yellow LEDs are on here, and that's showing us the inverted signal, which is currently high. If I flip one of these switches, it should change something. So we'll flip that one, and yeah, okay, there we go. My switches are in a inverse order compared to the LEDs themselves, but that switch you can see changes from the yellow LED to the red LED. This switch doesn't do anything because this switch is with our messed up one over here. So if we turn all the other switches on, oh, that's interesting as well. That one didn't light up either, huh? There we go. So our inverted one is working correctly on this one, but our non-inverted one is not illuminating. And then this one, the non-inverted one is always illuminated. So, well, that's how it goes sometimes. We've got a little bit more troubleshooting to do. So I'm going to troubleshoot that and see if I can figure out exactly what's going on. And then hopefully we can get everything working perfectly. All right, that was probably the easiest troubleshooting I've ever done in my life. The one over here that wasn't illuminating correctly was just a flaky connection with some of these jumper cables. The one up here, there was actually a tiny sliver of copper on the backside that was shorting the input trace to 24 volts. I just had to dig it out just a little bit, and well, here we go. Bam! It's working perfectly. So if I take all 6 bits here and flip them on, you can see all of our red LEDs turn on. If I take all 6 bits and flip them off, all of the red LEDs turn off and all of the yellow LEDs turn on. And so we have our 6-bit address being properly buffered, inverted, and buffered again. This is gonna work perfectly for what we need. That is very cool. So in the next episode, we're going to cut up the boards that take the 6-bit address and the inverted 6-bit address and decode it into the individual X select and Y select lines. And then we're going to plug those into some memory boards and hopefully give it a test and see if we can get it to store a bit of memory at a specific address. That's going to be a pretty wild milestone. So I want to thank you guys so much for watching, and I hope to see you in the next episode because that's going to be a fun one.